Welcome to the Sensorless Field-Oriented Control for AC Induction Motors web seminar. Hi, my name is Jorge Zambada. I am an applications engineer for the Digital Signal Controller division at Microchip. Here is the agenda for today's seminar. We will briefly talk about the induction motor's role in the industry, covering its main characteristics. Then we will talk about Sensorless Field-Oriented Control, or FOC, with a description of its functional blocks. We will conclude showing a side-to-side comparison of sensored versus sensorless results. In this section, we will briefly talk about ACIMs and their role in the industry. At least 90% of industrial drives have induction motors. This is a result of its robustness and low cost. Another important aspect is the low maintenance cost, which is a consequence of its simple and reliable design. An additional key factor is that the rotor does not have any moving contacts, which eliminates sparking. Some of the applications where we find ACIMs are pumps, fans, blowers, compressors, and industrial automation. In most cases, induction motors are used with drives that have little or no electronics at all. In the case of no electronics, the motor is directly connected to the power line or through a mechanical relay. From now on, we will narrow the field of induction motor type to the squirrel cage model. One of the main characteristics of this type of induction motor is the slip of the rotor speed with respect to the stator speed. For this reason, this motor type is also known as asynchronous motor. A demonstration of its operating principle is highlighted in the figure. As it can be seen, a conductor being part of the rotor is moving with speed omega 1 through the electromagnetic field moving with speed omega 3. With the directions indicated by the speed arrow. The resulting conductor speed relative to the magnetic field speed is omega 2, which is equal to omega 3 minus omega 1. A back electromagnetic force, also known as back EMF, will be induced with the direction of the blue arrow indicated in the figure. If the relative speed of the conductor with respect to the magnetic field speed is 0, no back EMF will be induced, and therefore no current will appear inside the conductor. The interaction of the current with the magnetic field will produce the electrodynamic force, F, shown with a green arrow. The rotating stator flux induces the back EMF in the rotor squirrel cage, which generates the rotor flux. The motor starts spinning as the rotor flux is trying to catch the rotating stator flux. The rotor will never be synchronous with the stator rotating currents because if they were to be synchronous, no back EMF will be induced in the rotor cage and no rotor flux is generated. In this section, we will talk about sensorless field-oriented control of an AC induction motor. First of all, we will have a brief description of the control system, and secondly, we will have a detailed description of sensorless field-oriented control. This is the general control scheme for sensorless FOC of an AC induction motor. Its two main blocks are 1. The DSPIC control algorithm block, and 2. The three-phase inverter with signal conditioning block. The purpose of the system is to control the speed of an induction motor using field-oriented control without any position or speed sensor. In the following slides, we will briefly describe the three-phase inverter block. The three-phase inverter and signal conditioning block is responsible for generating the three-phase sinusoidal voltages to the induction motor and for conditioning the feedback signals connected to the DSPIC. Main blocks are 1. Power electronics gate drive stage that handles high voltages to be fed to the motor windings. 2. The optocoupler's drive block, which is used to isolate digital and power grounds. The third block has a set of current sensors that provide the motor phase currents to the DSP. The fourth block has a fault detection circuit to disable all power outputs when an overvoltage or overcurrent is detected. And the fifth block has all the conditioning circuitry for the feedback and fault signals. We will now describe the sensorless field-oriented control algorithm. The key to understanding how field-oriented control works is to form a mental picture of the coordinate reference transformation process. If you picture how an ACIM motor works, you might imagine the operation from the perspective of the stator. From this perspective, a sinusoidal input current is applied to the stator. This time-variant signal causes a rotating magnetic flux to be generated. The speed of the rotor is going to be a function of the rotating flux vector. From a stationary perspective, the stator currents and the rotating flux vector look like AC quantities. Now, instead of the previous perspective, imagine that you could climb inside the motor. Once you're inside the motor, picture yourself running alongside the spinning rotor at the same speed as the rotating flux vector that is generated by the stator currents. Looking at the motor from this perspective during steady-state conditions, the stator currents look like constant values, and the rotating flux vector is stationary. Ultimately, you want to control the stator currents to get the desired rotor currents, which cannot be measured directly. With the coordinate transformation, the stator currents can be controlled like DC values using standard control loops. Let's take a look at the different components of field-oriented control. The transition of coordinates separates the current component responsible for the magnetizing flux of the motor, or ID, and the component responsible for motor torque, or IQ. In order to transition from the fixed reference frame alpha beta to the rotating frame, or D and Q, the position of the rotor is required. In sensorless control, the position is estimated as shown in the figure. We start from the right of this block set by measuring two phase currents, IA and IB. We can determine the third current assuming that the sum of the three currents is equal to 0. These two currents are then transformed into the fixed reference frame, or I alpha and I beta. Now, the rotor flux angle is needed for the transformation of the currents from the fixed reference frame, alpha and beta, to the rotating rotor reference frame, ID and IQ. The resulting transformed currents will be responsible for magnetizing flux, ID, and the torque, IQ. The transformation from the fixed to rotating reference frame is called Park transform and will be described later in the web seminar. I alpha, I beta, V alpha, and V beta will be used to estimate the position and speed of the motor. The speed error between the reference speed and the estimated speed is fed to a PI controller. The output of the PI controller will be the reference IQ, which is responsible for torque generation. Torque and flux are also compensated by PI controllers. D and Q voltages, which are computed in the rotating reference frame, are transformed back to the fixed reference frame using the inverse Park transformation block, producing V alpha and V beta. From V alpha and beta, a modulation technique called space vector modulation, or SVM, is used. SVM transforms the fixed stator reference frame voltages to signals that drive the power inverter. The first block to be described is the Clark transform, highlighted in the figure. The Clark transformation block converts the phase currents to fixed stator reference frame. The equations describing the transformation are based on the fact that the sum of the three phase currents is 0. The next block to be described is the Park transformation block. In this control topology, a direct and inverse Park transformation blocks are needed. Inputs to this block are the outputs of the Clark transformation block and the angle of the rotor. There are two directions of this transformation block: direct, from fixed reference frame to rotating reference frame, and inverse, from rotating to fixed. The equations indicated are simple trigonometric transformations from one reference frame to another. Direct part transformation outputs D and Q are time invariant in steady state conditions. D component is proportional to the flux, while the Q is proportional for the torque. The inverse part calculates the equivalent of input voltages from rotating reference frame to a fixed reference frame. We will move now to the estimator block description. The estimator's inputs are I alpha, I beta, V alpha, and V beta, and its outputs are the estimated rotor angle and the mechanical speed of the motor. The speed and angle estimator has as inputs the fixed reference stator frame, two axis voltages and currents. Back EMF is used to estimate speed and position. First of all, the induced back EMF is calculated. As it can be seen from these two equations, E alpha and E beta calculation is done. Since the estimation principle is based on the fact that the D component of the back EMF is 0 when the magnetizing current is 0, we need to calculate the D component of the back EMF to know the estimation error. This figure shows the DQ components of the estimated back EMF. The DQ components are obtained using the direct Park transformation block previously described. Since the angle is produced by the estimator itself, we will have an internal loop inside the estimator which will adjust the angle with a phase-locked loop. The mathematical model of the back EMF is presented here, which highlights its dependence on the magnetizing flux. Separating the space vector from the back EMF equation into D and Q components, it can be seen that ED is proportional to the derivative of the magnetizing flux. This is the principle of the estimator. No variation of the magnetizing flux will make the derivative equal to 0. The Q component of the back EMF is proportional to the magnetizing flux speed and the magnetizing flux. If the estimated back EMF is not equal to the actual back EMF, the angle between the estimated and the actual back EMF is delta theta, as shown in the figure. The figure shows the DQ estimated back EMF. If the estimated back EMF is not equal to the actual one, the angle between the estimated and the actual back EMF, or delta theta, is not 0, as shown in the animation. The estimator will correct the error in such a way that the estimated EQ is equal to the measured EQ. It can be seen that delta theta is decreased. In fact, the smaller the delta is, the closer the estimated and actual values are. This slide shows how the error is corrected when the D component of the back EMF is greater than 0. When the D component of the back EMF is less than 0, the angle error between the actual rotor angle and the estimated one is greater than 0. The estimator has to decrease the error in order to get the D component of the back EMF back to 0. A simple way to correct the error between estimated back EMF and actual back EMF would be to subtract the error, or delta theta, from the estimated angle. However, correcting the angle directly could lead to numeric instabilities. On the other hand, correcting the speed instead of the angle produces more stable results. Once the speed has been corrected, the angle is calculated by integrating the speed. When there is an error on the estimation, the D component of the back EMF will be different than zero. In fact, the bigger the D component of the back EMF is, the bigger the speed error is. This is the reason why we use the D component of the back EMF as the correction factor of the estimated speed. The sign of the Q component of the back EMF indicates the sign of the correction term. A positive EQ value corresponds to positive speed, and a negative EQ value corresponds to a negative speed. The table shows a summary of the correction factor used depending on the speed direction. This is a block diagram of the position and speed estimator. The back EMF alpha and beta are calculated using the corresponding voltages and currents with the equations indicated in the previous slides. The Park transform shown in the red block converts these values from fixed stator frame alpha beta into rotating frame dq. The angle used for this transformation is set to an initial value and then is dynamically updated with the estimation. The dq component outputs are filtered because they are computed from the current measurements, which can be noisy. The first order filter used should be fast enough to allow dynamic changes. The sign of the Q component of the back EMF is extracted and multiplied by the D component of the back EMF. Then, these two components are added to obtain the speed error correction. The result of the sum is divided by the magnetizing flux, and the result is the magnetizing flux speed. The integral of speed is the angle of the rotor flux, which is feedback to the Park transformation block, which closes the estimator's internal loop, as can be shown in the figure. The magnetizing flux value can be considered constant if the mechanical speed does not exceed the nominal value. If field weakening is to be used to operate the motor above rated speed, the magnetizing current needs to be dynamic instead of a constant. The next block to be described is the field weakening. This block is needed when motor operation above rated speed is a requirement. In applications where the maximum speed does not exceed the nominal speed of the motor, this block can be replaced by a simple constant equal to the D-axis current requirement, which is proportional to the magnetizing flux requirement. When exceeding the nominal motor speed, the rotor flux must be weakened. A mechanical speed increase will require a frequency increase of the stator currents, but this must be done with respect to the simple volts over Hertz equation. Since the voltage cannot be increased over the nominal value, the increase of speed must be done sacrificing the overall torque produced, keeping a constant power curve. The next block to be described is the PI controller block. The PI controller is the control loop feedback mechanism that corrects the error between the measured process variable and its reference value. In the case of induction motor control process, 3 PI controllers are used, one for each current component corresponding to magnetizing flux and the torque, and another one for the speed. The proportional term reduces the overall error to 0, but in most cases of control, a steady-state error will remain, and this error is removed with the integral term. The last block to be described is the space vector modulation block, or SVM. The SVM block generates PWM signals to the three phases of the motor. As indicated in the animation, each of the three inverter outputs can be in one of the two states, which allows a total of 8 possible states that the outputs can be in. When all three outputs are connected to plus or minus voltage, the state is considered null because they do not generate line-to-line voltage. The other generated states are separated 60 degrees from each other, as shown in the animation. The SVM produces all the other voltage vectors as a sum of two adjacent vectors. The linear combination of the two vectors is reflected in the duty cycles of the generated PWMs for each phase. In summary, we have discussed basic characteristics of an AC induction motor. We've discussed each of the field-oriented control blocks, including a more detailed discussion of the angle and speed estimator. The experimental results prove that there is no significant difference between the step response of the sensorless control and the sensored control. The estimator can replace a position sensor without sacrificing dynamic response of the control. As shown in the figure, on the left side we have the step response of a sensored control using an optical encoder, and on the right we have the step response of the sensorless control, where speed and position are estimated. With these results in mind, we conclude that sensorless FOC control benefits applications where dynamic response and efficiency are required without addition of expensive position or speed sensors. We have application notes on motor control. These documents can be obtained from Microchip's website by clicking on the DSPIC Digital Signal Controllers or Technical Documentation link. We also have a Motor Control Design Center at www.microchip.com/motor. This wraps up the seminar on sensorless field-oriented control of AC induction motors. Thank you for your interest in the DSPIC Digital Signal Controller.